about frames. We are done with frames, chapter 5. We start chapter 6, talking about plane stress and plane strain. And then we will continue this next week also. So this week and next week, chapter 6. Let's go to, I clicked on the wrong. Let's go to document plane stress and plane strain. This is what we are going to discuss today. We are going to talk about basically triangular elements, the simplest type of two-dimensional elements. Plane stress and plane strain problems, these are two-dimensional problems. At the beginning, question for you. At the beginning of this term, we said that there are two types of elements. Anybody remembers what these two types are? At the beginning of the term, we said we have two types of elements in finite element methods. One of them, we said it is structural elements or line elements. What is the other one?
Continuum elements.
Continuum elements. Very good. You're right. Continuum elements. Continuum elements are two-dimensional or three-dimensional elements. Unlike the structural elements, which were line elements, we use them for trusses, for beams, for frames, for bars. But these are two-dimensional or three-dimensional elements called continuum elements. So the two-dimensional elements that we use are triangular elements with 3 nodes, triangular elements with 6 nodes, and so on and so forth. So today we are going to discuss continuum elements, two-dimensional. But first, an introduction to plane stress and plane strain. What are these two, plane stress and plane strain? Well, these are two-dimensional, as you see, plane. Everything is in one plane. Let's say it's in XY plane. Plane stress, you had these definitions, of course, in your strength of materials, I think. So I will go a little bit like a review. I'm going fast. Plane stress, it is just an example of this is like this beam, this cantilever beam in XY plane. The assumption is that these are thin. The thickness of this, which is perpendicular to the screen, it is so thin that stress doesn't vary through the thickness. It is very thin, so stress doesn't change. So there is nothing happening in the Z direction. Everything is in XY plane. The load is in XY plane. So with this situation, our state of example cantilever beam with very thin, for example, I think with thin thickness, this is our XY plane. This is a state and stress element. Stresses are sigma x, sigma y, and tau xy. So 3 components of stress. Everything is in one plane. So everything in the Z direction, 0. So it means sigma z, tau x z, tau y z, these are all 0. So our stress vector consists of this sigma x, sigma y, tau xy. That's what you see here. Epsilon stands for what? Anyone?
Strain.
Strain. Epsilon x is normal strain in the x direction. Epsilon y is normal strain in the y direction, and gamma xy is shear strain. These are the components of strain we have. We have also epsilon z. It is plane stress. Doesn't mean plane strain. So plane stress means that no stress in the z direction, but we have a strain in the z direction, which is given by this. It is negative nu over E sigma x plus sigma y. Nu stands for what? Here, anyone?
Is it the Poisson's ratio?
Poisson's ratio, very good. So this is the strain in the z direction. Now, so this is our stress. These are our strains, including also this one. Now, stress and strain are related by Hooke's law. So Hooke's law relate them by a matrix D. D is called material matrix, as you see here. This is a material matrix, and for plane stress problems, it is given by this. This is a 3 by 3 matrix. This is E, and this is nu, and it is symmetric. As you see, this is the same as this. This is the same as this. This is the same as this. So this is a symmetric matrix, very helpful in our computations to reduce the number of computations and memory usage. So this is plane stress. Now, plane strain, on the other hand, these are structures which are usually long, actually. Like, for example, this is a cross-section of a dam. You see the water pressure behind the dam. This is the XY plane. So Z direction perpendicular to this is where this dam continues, and it is attached to, let's say, a hill or a mountain here and another hill here. So this is usually a long structure. One slice of this unit thickness slice of this is a good example of a plane strain problem. Like pipelines, for example. Pipelines are also long. So one slice of this is an example of a plane strain problem. It is plane strain because you see this is fixed at this end of it is attached to a hill here and they are attached to a hill here. These hills do not move. So it cannot move in the Z direction. So it is strained, it is constrained on both sides in the Z direction. So it is a plane strain, meaning the strains that we have are epsilon x, epsilon y, gamma xy. All other strains like epsilon z, gamma xz, gamma yz, all of them are 0. No index of z, everything 0 with these indices of z. The only strains we have are this. Stress also given by this, stress also sigma x, sigma y, tau xy, but there is a stress in the z direction. And it is given by this nu sigma x plus sigma y. These are all from Hooke's law. Again, stress sigma and epsilon are related by Hooke's law, and it is by a material matrix D, which for plane strain problems, it is given by this. Again, a 3 by 3 matrix, and it is symmetric. You see, this is the same as this. This is the same as this. Oops, and this is the same as this. So this is a symmetric matrix also. Now, one question for you before finishing this discussion. We can run into a problem here. There is something which is a little alarming. What is that? What can go wrong here? Anyone?
It could be undefined.
When is it undefined? You're right, but when is it undefined? When what happens if nu is 0.5? If nu is 0.5, what happens?
We have
Dividing by 0.
We have
Yes,
0 in the
denominator is 0, so divide by 0, it is singularity error. So the program cannot handle this, suddenly divide by 0. So when Poisson's ratio is 0.5, we always have a little bit problem in finite element method. Sometimes you have to check the program, see if they can handle this case or not. Sometimes some programs you give Poisson's ratio of 0.5, the system can't proceed because of this situation here. As you see, we run into serious problem. But the point is that actually in almost all cases, Poisson's ratio is never 0.5. Poisson's ratio is usually a number between 0 and 0.5, less than 0.5. So, but 0.5 itself causes problems here. Poisson's ratio of 0.5, meaning that the material, if you apply pressure on all sides of, let's say, a cube, then the material, after the stress exceeds the yield strength of the material will expand. But it's not possible when you apply a compressive stress on a stress element like a cube, material shrinks, like volume dilatation that you had in your strength of materials. But Poisson ratio of 0.5 means material expands, but it's not possible. So physically, it's not possible to have Poisson ratio of 0.5, but some materials like elastomers, sometimes some of these new materials which we have, it is possible that they behave in a way that we have to be more cautious about them. Sometimes even Poisson ratio can be negative. Some materials, you stretch it in the x direction, it also expands in the y direction. So these are very, very rare cases, of course, like foam, for example. You stretch it in the x direction, it also expands in the y direction, which is very unusual, but it's very special cases we have to pay attention. Now, constant strength triangular element. This is the subject of our discussion today, actually. This is a continuum element. This element, a little bit patience, we go through this and then we look at one example problem and we are done with our lecture today. This is a triangular element. It has 3 nodes. Node I with coordinates x, I, y, I. Node J, coordinates x, j, y, j. And node M, coordinates x and y, m. Each node has a displacement in the x direction, ui, for example, for this one, and the displacement in the y direction, vi. The same for this one. This is node J. It has a displacement uj, vj. Node M, um, it's not showing, and vm. So each node has 2 degrees of freedom. How many nodes does this element have? Anyone?
3.
3. How many degrees of freedom per node?
2.
2. So 3 times 2 degrees of freedom per node makes it 6. So our element stiffness matrix should be 6 by 6. Now, another item to pay attention, always call this element counterclockwise. Label this counterclockwise. So call this element IJM. Do not call this element IMJ. Don't go clockwise. Our formulations are not written in clockwise direction. They are all formulated counterclockwise. So call this, you can start from anywhere, for example, call it JMI. So go counterclockwise. This is our displacement vector. It consists of UIVI, UJVJ, UMVM. 2 degrees of freedom per node. This is our displacement vector. Now, as what we were always doing, the formulation is very similar path. So I go a little bit faster but whenever you have questions, always feel free to ask. But the same procedure, we start with the displacement function. This is our displacement function. U is displacement in the x direction, a1 plus a2x plus a3y, and v, displacement in the y direction, a4, a5, a6. So these are the displacement in the x direction given by this equation, in the y direction given by this. We said how many unknown, how many degree of freedom that this element have with what we discussed. How many degrees of freedom do you see here?
6 total.
6 total. It matches with this 6. Always the number of degrees of freedom of the problem element matches with the approximation function that we start. Again, the same procedure, we apply the boundary conditions and find A1, A2, A3 up to A6 and put it back to find U and V. That's what we want to do. So apply the boundary conditions. At node I, U, displacement in the x direction is UI. So put the coordinates of x, I, y, I. At node J, U, displacement in the x direction, it is UJ. These are coordinates of this, and the same thing for at xm, and the same thing for V at node I, at node J, at node M, 6 equations, 6 unknowns, solving for A1 through A6. It's a little bit more involved here. So the result is this. You see a lot of alphas, betas, gammas. These are the parameters that are, which are defined by this. So these alphas, betas, and gammas, these are in terms of coordinates, nodal coordinates of node I, J, and M, as what we see here. All of them are in terms of these coordinates. So these are the alphas and betas and gammas. It is more convenient to write them like this. Otherwise, it's a little bit lengthy. And this 2A, you see 2A here. A is area of this triangle. This triangle has an area. Area is given by this. Twice the area is actually determinant of this, which is the same as alpha I plus alpha J plus alpha N. So these are all just parameters, alpha, beta, gamma. If you open, for example, FEMAP, you see the same, they call them alpha I, alpha J, alpha M. So these parameters are programmed, they follow the same. So we find these A1 through A6. A1 through A6, put them back into this equation for U and V. We find U and V to be given by this. That's what we wanted. This is U. I can highlight, cannot highlight this one, but both of them, this is U and this is V. That's what you see here. This is alpha again, beta I, gamma I, sometimes multiplied by UI, multiplied by UJ, multiplied by UM, the same VI, VJ, VM. So this is U and V. We can write them like this. This U we can write, we call this one NI, as you see, NI-UI plus NJ-UJ, this is this one, NJ-UJ plus NM-UM. And the same for V, NI, NJ, NM. Question for you, in this class, we use N for what?
Shape functions.
Shape function, very good, you're right. Shape functions are, we show them by NI, so in this case, NI, this is NJ, this is NM, and these are here, NI, NJ, NM. They play an important role in finite element methods. These are shape functions. And remember, they have some properties, NI, NJ, NM. N, each shape function has a value of 1 at its own node and it is 0 at the other node. So, and always they add up to 1. So Ni plus J, Nj plus Nm is 1, and N is 1 when it is evaluated at its own node, and it is 0 at other nodes. So the same shape properties that we remember we discussed before. Ask the question, show that Ni is equal to 1. Show that Ni is equal to 1. You have 2 minutes. This is Ni. This is Ni. Write it down. You have your paper and pencil ready. Write this one down. Ni is equal to 1 over 2a. Alpha I plus beta Ix plus gamma Iy. Show that if you evaluate this at node I, it would be equal to 1. So I'm also writing it down here. All right, so write this one down here. I want to show that when, if I evaluate this at node I, it would be equal to 1. So let me Let me see. Do you see the camera here?
Yeah, we can see it.
Okay, very good. So you see this is Ni is equal to 1 over 2a alpha I plus beta Ix plus gamma Iy. I want to evaluate this to make sure that at node I want to check to see if it is equal to 1 or not. Ni is equal to 1 over 2a. 2a, remember, we said it is alpha I plus alpha j plus alpha m. If you keep alpha I plus, now here we have, of course, I wanted you to do this, but I will just start this one here. So this one is beta I. Beta I, it is evaluated at xi. So I multiply xi by beta I. But beta I is yj. It is yj xi minus ym minus ym xi plus this is gamma I y. So gamma I is xm y I minus xj y I. I want you to become familiar with these alphas, betas, gammas that we have. That's the purpose of this practice here. Now, if you look at this, can you tell me yj? Of course, you have to look at those definitions that we have for alpha, betas, and gammas. You see that yjxi minus yi xj, this and this, these two, let me double line, these two, this is actually alpha m. This and this, it is alpha m. And this one, xmyi, this one, let me show it with xmyi minus ymxi, this one and this one, these two are alpha j. So actually it is 1 over alpha I plus alpha j plus alpha m, and it is alpha I plus, again, alpha j plus alpha m. If we add them, this one cancels with this. It is actually 1, and that's what we wanted to check. So yes, if you evaluate at Ni at node I, it is equal to 1. And you can check that, make sure that, for example, if at other nodes, if you put at node j, so it would be xj, yj, it would be 0, and I would be 0 if it is evaluated at other nodes. So you can show it yourself. All right, I just checked this one, but you can check others. Any questions on this before moving on? All right, let's go back to our, so this is the one at its own node, and it is 0 at other nodes, and they add up to 1. And as a practice, I wrote these things down. You can practice these items yourself. Let's quickly look at these formulas and then look at one example problem. Using the strain displacement relationship, you see epsilon strain is related to U by this. These are called strain displacement relationships. Epsilon x is this, epsilon y is this. It is derivative of v, displacement in the y direction with respect to y, and it is shear strain. So epsilon is this actually, derivative of u with respect to x, derivative of v with respect to y, and similarly to this one. But U and V, we already have them. You see, we found this is U and V. That's what we wanted. We found, so we can find the strains. Derivative of U with respect to X is epsilon X. It is this. Derivative of V with respect to Y is epsilon Y. It is this, and this is gamma XY. If we do this in matrix form, it is actually our epsilon is given by this. A matrix multiplied by this displacement vector, Ui, Vi, Uj, Vj, Um, Vm. This matrix, it is called B matrix or gradient matrix, some people call this one. This is the, we multiply it by displacements, then we can find the strains. So epsilon is equal to BD. This is this, epsilon is BD. B is this matrix. But the stress and the strain are related. Once we know strain, we can have a stress. Stress is sigma times D times epsilon. Or sigma is D times epsilon, which is BD. So D, BD. This is stress. All right, so that's what we wanted to find. This is epsilon and this is sigma. All of them related to this B matrix, which these are betas, beta I, beta J, beta M, and gamma I, gamma, beta I, gamma J, beta J, and so on and so forth. But we have not found the element stiffness matrix. That's what we are going to do next week. So here, let's look at this example problem quickly and see how we can find, assuming we know D displacements, that this is Nastran's job is supposed to find for us. We will see how, because for this, to find this, we need the element stiffness matrix. Let's find stress. Suppose we know this now. Let's apply this formula and find the stress in this problem. In this example problem, we have this triangular element, this node I. You can call it node 1, node 2, node 3, or IJM. So this is the element. Coordinates are given. X and Y coordinates are given for each node. We want to evaluate the stiffness matrix. We cannot do this. We didn't discuss this, so we will discuss this on Monday next week. Assume we have the displacements U1, V1, U2, V2, U3, V3. We know the displacements, modulus of elasticity, and Poisson ratio. We want to find determine the element stresses. We want to find stresses sigma X, sigma Y, and tau XY for this element. Well, to find the stresses, we use this formula. Sigma is dBd. D is the material matrix. And this B is this matrix. We need to find it. So these are all betas and gammas. So that's it, for example, for this element. These betas, these are the gammas. Beta I is Yj minus Ym. So we know the coordinates, we can subtract them. This is beta I. This is beta J. This is beta M, and gamma is the same. So our B matrix is this. As you see, these are all numbers. These are all constants. So in this matrix, all of them are just some numbers. They are not functions of X and Y. So if they are all constants, and these are all displacements also, displacements are also numbers, these are constants. So it means that our strain will be constant over this element. That's what you see, this element. This element is called constant strain triangular element. This is the simplest type of element. Because of this behavior, it's called also CST element or constant strain triangular element. Because of this behavior, as what you see here, this strain, these are all constant. So this strain over the element will be constant. That's what it is called, CST element or constant strain triangular element. So this is the B matrix, all constants. This is material matrix. Suppose this is plane stress. Remember, for the material matrix, we had plane stress option and plane strain option. So suppose this is plane stress. It is given by this. Remember, let me quickly also show plane stress here. Plane stress, we said that this is this matrix, D, material matrix. So this would be, our stress would be dBd. This is material matrix D. This is B. This is K. We do not discuss this. We will discuss this later. So stress would be D, material matrix, B matrix, and D matrix, displacement, nodal displacement that we are given. If we multiply this, we find stresses to be like this: sigma x, sigma y, and tau xy. Now, as you see, these stresses are constant. What do these stresses mean? Where is this 19,200 psi? Sigma x is 19,200. On this element, where? Question for you. This 19,200 psi. Where is it? This is sigma x. Where? Here at this node? At this node? Here? At the centroid?
Constant over the full element.
I'm sorry, once again?
Constant over the full element.
Constant over the element. Very good. You're right. So that what makes this element very actually small, simple, because if strain is constant, you see strain and stress are related here. If this strain is constant, this BD is a strain. So if this is strain, so you multiply by another constant, then the stress will be constant. So for this element, stress over the element becomes constant. So it doesn't change anywhere. That makes this very simple and easy to formulate, because we didn't, in other more advanced types of elements, it depends on at what point you want to find the stress. It usually uses Gaussian points or at the centroid of the element somewhere, but this is everywhere. So if this element is very large, for example, in a finite element analysis of a structure, if this element is very large, so finding a stress, constant stress over this large element, it's not correct. Sometimes the stress gradient is high, stress changes rapidly, so we cannot have very large element and having the same stress everywhere. So this is our stress, and as you see, it is D matrix, material matrix, B matrix, and or the gradient matrix, it is called nodal displacement, and these are the stresses which are constant over the element. And here the author also goes and finds the principal stresses, which is sigma x plus sigma y divided by 2 plus from strength of materials finding principal stresses. All right, so today we discussed plane stress, plane strain problems, and also we defined this very important item, constant strain triangular elements. We found that stress becomes constant over the element. Strain also is constant over the element. All is because of the behavior of this B matrix, which everything, these betas and gammas, they are all constants. It is not the case for more advanced types of elements, like we have another version of this triangular elements with mid-side nodes. So there is one node here, one node here, one node here. That element is behaves differently. That element, it depends at what point you want to find the stress. But for this 3-node triangular elements, stress and strain become constant over the element. But for more advanced type of element, it is called nonlinear triangular element. This one sometimes it's called linear triangular element, or 3-node triangular element. Stress and strain become constant. But for the other one with 6-node triangular element, it is not, and it requires much more computations. We have to go and each one of these terms, the B matrix, each one of these terms is a function of X and Y. So we have to go and numerically integrate, which is a little bit time consuming for those problems. All right, I do not want to go into more than this about the how to find the element stiffness matrix. We have to use principle of minimum potential energy, like what we did before for a bar subjected to generalized loading. We used principle of minimum potential energy to find the very important formulas, including the element stiffness matrix. We do the same thing here. This is variational method. Unlike the direct method, this is variational method, more powerful method in finite element formulations. Total potential energy is strain energy, U, plus potential energy due to body forces, plus potential energy due to concentrated nodal forces, plus potential energy due to on the surface or traction surface forces. All of them together creates the total potential energy. This total potential energy has to be minimum, as what you see, minimum potential energy. For a structure to be in equilibrium, its potential energy must be minimum. So on Monday next week, we are going to find this pi, substitute this is U, this is omega P, omega B, this omega P, and this omega S. We put them here, manipulate with these formulas, make some substitutions, and then minimize this with respect to displacement, and we derive very important formulas. That will be our task for next Monday. This Wednesday in the lab, we are going to, I will give you the project. We are done with three-dimensional analysis. You did it 3 times for the past 3 weeks. 3D analysis is when we want a more accurate and more detailed analysis of a structure. So we did it 3 weeks for the past 3 weeks, 3 exercises. On Wednesday this week, I will give you a project. So you are going to work on that project for the rest of the semester. All right, I will stop here. Any questions, anyone? All right, no questions. I stop here. Have a good rest of the day, everyone. I will see all of you on Wednesday in the lab. Take care, everyone.
Thank you, Professor.
Thank you.